This is an aid to chapter 6 of ME143 Introduction to Fluid Mechanics, and this video summarized the main parameters and equations for internal flows. The very first parameters that you need to calculate or estimate when dealing with an internal flow, and here we are talking about a pipe flow in particular, is the Reynolds number. And your Reynolds number will be defined for all the correlation that we will use in the future by the bulk velocity VB, the pipe diameter, the viscosity mu, and density rho. So the viscosity here is the dynamic viscosity, and remember that the kinematic viscosity is mu over rho. And then this is not part of the Reynolds number, but nonetheless very important. The epsilon will be the pipe roughness. Now here note that I have defined the bulk velocity as a function of the mass flow rate and the flow rate, and given also the equivalent definitions of the Reynolds number. Once you have the Reynolds number, you can define what type of regime you are dealing with. Oops, sorry about that. Let's go back. Here we go. The different regime that you are dealing with. So for Reynolds number of the order of 2000, this is the critical Reynolds number C. Below that, you can expect the flow to be laminar. And above that, you can expect the flow to be turbulent. Now this is a very simplistic classification of flow, but one that works fairly well for most flows. In fact, most enduring flow will be much larger than 2000 and definitely turbulent. Once equipped with the knowledge of your flow regime, you can determine the length of your entrance flow. Remember that the entrance flow is that region where the boundary layer grow and eventually merge. And so if you have a laminar flow, you're going to use this correlation, and if you have a turbulent flow, that will be the second correlation. We will see in just a minute why we need this information. So now, to the really interesting part of the problem: how do we calculate the energy that is lost through the flow in a pipe, or with valves? There could be a pipe network, but anyway, an internal flow system. This is a 1D conservation of energy equation with correction for the velocity epsilon depending on alpha depending on the regime of the flow. Now, the energy in A is transformed to energy in B plus the losses, and the losses due to friction, and the losses due to minor or to singular losses, valve, pump. Also, if there is a pump, obviously it's not a loss, it's a gain. But I think that's pretty clear to everyone. Now, friction losses are defined by this relation, and here L is the length of the pipe, D is the diameter of the pipe, G is the gravity, F is the friction factor, and sorry about that, I didn't mean to zoom, friction factor. An alternative definition of F is given here, not the most useful for you, but here's why it's very important to know in which regime of the flow you are, not only laminar and turbulent, but to know if you are fully developed. The correlation that we have are only defined for fully developed flow. For laminar, we have F equal 64 over RD, and this is exact. That's derived from the Poisson velocity profile. For turbulent, we have the Moody diagram, and that's an empirical correlation. So for entrance flow, we don't know, and that's why you want to remember those correlation of the length of the entrance flow to demonstrate that in most cases that region can be neglected. So this is the Moody diagram, and the Moody diagram plots the friction factor as a function of the Reynolds number and the roughness of the pipe. And so you can use that, let's say, if you know the Reynolds number and the roughness of the pipe, you can get the friction factor and therefore the head loss. Minor losses deal with any change in geometry due to pipe entrance or exit, sudden expansion, bends, valves, and their definition is the following one, where K is a coefficient given by charts and table, and also can be measured with this relation, where delta P is the pressure drop across the device that creates the minor loss. So to finish, what how do we actually solve practical problem? If you have a serial network of pipe, meaning a subsequent series of pipe, then with singular connection between all of them, then the total head loss is the sum of all the minor losses and the friction losses. If you have a parallel network of pipe, you need to consider the fact that, for instance, like let's say you have point A and point B, and you have a series of pipe 1, 2, 3, and so on, then the head loss should be the same for all those pipes, and now you have a system equation to solve for whatever you want to deal with. What happens if you have non-circular duct? Well, you're going to define, instead of using D, the diameter of the pipe, now you're going to use the hydraulic diameter, which is defined as 4 times the cross-sectional area of the pipe divided by the perimeter. And surprisingly enough, you can still use the same correlation with a certain loss in accuracy, and that uncertainty very much depends on the shape of the pipe, but it's somewhat reliable. So this is it. I'll leave you with the last slide, how to solve an internal flow problem, and hopefully that's all you need.